Class example 2.34 will ask us to use not only our integral zero theorem and factor theorem, but will also challenge us to bring in some of our knowledge from Math 20-1. We're given a polynomial function f of x equal to 2x cubed minus 13x plus 10. And first we're asked to fully factor this polynomial. So using our integral zero theorem, we determine that the factors of the constant term 10 are plus or minus 1, 2, 5, and 10. This means that our possible factors would be x minus 1, x plus 1, and so on. Now, here we've shown an example of us testing p of 1 and finding that its remainder is not 0. We'll repeat this for some other values. We finally find that p of 2 gives a remainder of 0, and this confirms that x minus 2 is a factor. Well, this guess and check method was very helpful back before calculators were as efficient as they are, because it meant we only had to check certain values, in this case 8 potential values, instead of an infinite number of integers. However, in the age of the graphing calculator, here it's not really good use of your time to guess and check all the values. In fact, you might make a little arithmetic error and miss one of the right numbers. Better is in your calculator on the y equals screen, type in the function 2x cubed minus 13x plus 10. Check in your table of values. What x values output 0? Those are the zeros of the function, and you know how those correspond to the factors of the equation, of the function. You could also look at the graph and determine the x-intercepts. If you find integer intercepts, well, that's going to give you an easy factor to pull out. So here, you would either find an x-intercept at 2, 0, or by using the table of values, you'd see that when x is 2, the output is 0. And both of those would be equivalent to using this more rudimentary and by hand version of the factor theorem. Now that we know x minus 2 is a factor, let's divide it out of our given polynomial. We'll use synthetic division. Because the polynomial is cubic but is missing a squared term, we'll put a 0 for that coefficient. We find our remainder of 0, which confirms that x minus 2 was in fact a factor. The quotient represents the quadratic, which is the other factor in the polynomial. So we can say that p of x in its factored form is 2x squared plus 4x minus 5 times x minus 2. At this point, we try to factor the 2x squared plus 4x minus 5. But we find that it does not factor well, or does not factor using integers. So we will stop here. Now that we have this factored form, we're asked to determine the exact zeros of p of x. Notice the word exact. We will not be using decimal numbers, and so using our graphing calculator won't be enough here. We know that the 0 from the factor x minus 2 will simply be 2. But do any zeros come out of the quadratic factor? Well, we'll need to use our quadratic formula here. Using a, b, and c as 2, 4, and negative 5, we sub this into the quadratic formula and reduce it. Notice that our entire radical of root 56 can be simplified into a mixed radical. At this point, we have a common factor in the numerator, which simplifies with the denominator. This has given us 2 different exact zeros for our polynomial function. So our 3 zeros are the 2 coming from the x minus 2 factor, and then, as the quadratic formula states, negative 2 plus root 14 over 2, and negative 2 minus root 14 over 2. If we were asked to determine the exact roots of the equation 2x cubed minus 13x plus 10 equal to 0, well, those would be the same as the zeros of the function. Remember that the zeros of a polynomial, which in this case is f of x equals to 2x cubed minus 13x plus 10, are the same as the roots of the equation 2x cubed minus 13x plus 10 equal to 0.